Skew-symmetric matrix. Any matrix A, we write it generally as Aij n cross n. We know very well that these concepts are valid for square matrix. Okay, so if any matrix A is called a skew matrix if and only if this condition is satisfied, that is A transpose equals to minus A. If you do this transpose of any matrix and if it comes out to be the negative of that matrix, then we will call that matrix to be a skew symmetric matrix, just the opposite of symmetric matrix. So let us consider an example out here. Any matrix A, we have 0 minus 1 minus 4 1 0 3 4 minus 3 0. Just find the transpose. How to get the transpose? Convert the rows into columns. So first row, that is 0 minus 1 minus 4 is written vertically. Second, 1 0 minus 3, which was horizontally, I have written it vertically. And then 4 minus 3 0 written horizontally is written vertically. So here if you take minus common, you will get the same matrix as the previous one. Okay, and hence we can say that this matrix is a skew symmetric matrix. Now you'll be asking questions, sir, do I need to find the transpose of each and everything? No, the easy method is just check these two conditions. If these two conditions are satisfied, then we can say that this matrix given is a skew symmetric matrix. The first condition is, for a skew symmetric matrix, all the diagonal elements have to be 0. Unless and until all the diagonal elements are 0, you cannot just forget that it will never be a skew matrix. Okay, for any skew matrix to be there, the diagonal elements have to be 0. First condition. Second condition is Aij should be equal to minus Aji. That means if you are interchanging this with this, this with this, and this with this, you will get the negative sign. Okay, so this is your mirror, and the mirror elements, that is 1 is having the mirror image at minus 1, 4 is having the mirror image at minus 4, minus 3 is having a mirror image at 3. If all these two opposite elements are having opposite signs, then we can say that this is a skew symmetric matrix. Now there are certain properties. If A and B are skew symmetric, then we can say that A to the power of n is symmetric if n is even, and it is skew symmetric if n is odd. Let's check. I'm telling that A to the power of n is symmetric when n is even. So I'm not sure whether whether this A to the power of n is symmetric or skew symmetric. The only funda is that you need to find the transpose. So I can write A power n whole transpose. So I can interchange it. A transpose whole to the power of n. This could be written as minus A. Why? Because I have assumed that A is a skew symmetric matrix. So instead of A, I can simply write minus A. Okay, so minus A whole to the power of n, take minus 1 whole to the power of n outside, and then multiplied with A to the power of n. So here if you put n as even, you'll get this as positive, and here if you put n as odd, then this will be negative. Okay, so and hence we can say that A to the power of n is symmetric if n is odd, and it is skew symmetric if n is even, it is a symmetric, and if n is odd, it is a skew symmetric. Now the linear combination of the matrices is also skew symmetric. AB is a skew symmetric if BA equals to minus AB, or AP plus BA equals to 0, which is a null matrix. Now AB plus BA is symmetric, and AB minus BA is a skew symmetric. And for any square matrix, A minus A transpose is always skew symmetric. These all seems to be quite confusing, isn't it? So I suggest you don't remember all these statements. What do you need to remember? You need not to remember anything. Remember only this one, that is the first condition. If you want to check if any matrix is a skew symmetric, simply find the transpose. If you are getting the negative of the initial matrix, then you can say that it is a skew symmetric, otherwise it is not. Okay, so here if you want to check, simply get the transpose of this and check whether it is you are getting symmetric or skew symmetric. Okay, so that's it. See you in the next lecture. Till then, bye.